Courses in the cement industry. Present to you. In this course, you will see the most important Introduction to Kiln Control, Operator Development, Combustion, Presentation and Instructor Notes. Introduction. Today's state of technology within the field of electronics has enabled the cement producer to automate important parts of the cement manufacturing process. An example of such successful automation is the raw meal preparation, which in many modern cement plants is now fully controlled by X-ray analyzer and computer. A simple proposal for computerized rotary kiln control is outlined. However, the difficulties arise already when it comes to procure the necessary operation parameters. Some of the more important ones are hard to monitor continuously in a reliable manner. Although, for instance, accurate and reliable gas analyzers are available, it is difficult to sample the rotary kiln gas, due to the severe conditions prevailing at the inlet end. Also, it is noted that the burning zone conditions are not directly accessible for measuring, but are reflected in the clinker quality only after a substantial delay. Combustion learning objectives. To understand the mechanism of combustion, and be able to 1. Discern between the three types of firing systems. 2. Define combustion air, and components of combustion air. 3. List three main flame characteristics, and how they can be controlled. 4. State importance of fuel and air mixing, and variables to control mixing. 5. List three main indicators of combustion state, and how they can be controlled. 6. State the main goal in combustion control. Combustion. A. Definition of combustion. 1. A rapid oxidation of a combustible with the release of heat. 2. A reaction between fuel and oxygen, air. B. Requirements for combustion. 1. Sufficient oxygen, combustion air, to mix with fuel. 2. Efficient mixing of fuel and air. 3. Heat to ignite fuel. Combustion air. 1. The amount of air necessary to efficiently burn at a certain fuel rate. 2. Combustion air consists of primary air and secondary air. Combustion air consists of 1. Primary air. It includes 1. Primary air fan. 2. Solid fuel transport air. 3. In leakage. 2. Secondary air. It includes air from cooler. We follow together combustion air. See this video. 1. Primary air. 2. Secondary air. Combustion air needs. 1. Neutral combustion air. Practically impossible to achieve due to poor mixing of fuel and air. 2. Excess combustion air. A. Complete combustion. B. Too much air results in heat loss. 3. Lack of combustion air. A. Incomplete combustion CO. B. Loss of efficiency. 4. Adequate combustion air. Low CO, and low O2, at rotary kiln exit. Types of firing systems. 1. Direct firing system. 2. Semi-direct firing system. 3. Indirect firing system, newest technology. Direct firing system. 1. One fan to vent the mill, convey the coal, classify the ground coal and blow it into the rotary kiln, no control of flame shape. 2. All moisture goes to kiln. 3. High primary air, 30 to 35% of combustion air, resulting in high SHC. 4. Relatively safe, simple operation and low capital cost. Semi-direct firing system. 1. 2 fans to classify ground coal, and to blow the fuel into the rotary kiln. Can add additional fans for flame shaping. 2. All moisture goes to kiln. 3. Low primary air. 4. Higher capital cost than direct firing system. Indirect firing system. 1. Coal is ground in a separate system. Moisture removed from system. 2. Pulverized fuel bin, with high precision metering system. 3. Primary air is low. Blowers, low volume, high pressure, added to control flame shape. 4. Highest capital cost, safety and environmental issues. Combustion air in indirect firing system. Combustion air. Consisting of A. Primary air impulse. 1. Almost 4%, from axial air. 2. Almost 2%, from swirl air. 3. Almost 9%, from fuel transport air. 4. Plus in leakage. B. Secondary air. Almost 85%, from all air. Primary air, momentum. 1. Required to drive flame. 2. High momentum shortens, stabilizes, and compacts the flame. Momentum, that is, it means turbulence at burner tip. Noticeable. Higher turbulence results in better mixing of fuel and air. Primary air, axial and swirl air. A. Axial air. 1. Minimum flow to cool down the burner pipe. 2. Increase or decrease the flame temperature, which changes flame length. B. Swirl air. Increase or decrease the mixing of air and fuel, allowing a higher or lower flame temperature, which changes the shape of the flame. Primary air, transport air. Transport air. 1. For solid fuel transport only. 2. Does not vary with fuel flow. 3. Must be at the minimum flow. 4. Sufficient velocity at burner tip is required for flame momentum. 5. For solid fuel transfer, velocity should be 24 to 30 meter per second. Too low transport air lead to the fuel deposition. Too high transport air lead to abrasion and wear. Primary air in leakage. In leakage at the rotary kiln hood. 1. An expensive nuisance. 2. Significant impact on rotary kiln production, rotary kiln stability, flame length, specific heat consumption and ID fan capacity. Secondary air. 1. Heat recuperation. Higher SAT lead to lower SHC. 2. Flow controlled by ID fan. 3. Temperature controlled by grate speed. Clinker bed depth. 4. Kiln pressure. 1. Low is better for heat recuperation. 2. Air in leakage increases, with more negative pressure. 3. Constant kiln pressure, lead to stabilizes flame. Secondary air. 1. How much secondary air is required? Total combustion air required minus primary air. 2. Where is it coming from? From the hottest cooler chambers. 3. Impact of secondary air on flame. Low SAT lead to long, lazy flame. Mixing of fuel and air. Variables to control. In 2 ways. 1. Pulverized solid fuel. Fineness. Moisture. 2. Natural gas. Gas pressure. Fuel oil atomization by 1. Pressure. 2. Temperature. 3. Viscosity. Faster, more effective mixing by efficient combustion. Ignition. 1. Fuel ignition point. Temperature at which fuel ignites spontaneously, and starts to burn. 2. Flame ignition point. The point just after the plume, where the brilliant part of the flame starts. 3. Factors affecting flame ignition point. Depend on 1. Secondary air temperature. 2. Type of fuel. 3. Design of burner. 4. Design of kiln. Flame. Explain in this part. 1. Definition. 2. Temperature. 3. Heat transfer. 4. Shape. Flame definition. 1. Controlled combustion, burning, of a determined fuel. 2. All flames have a short plume of air and fuel. 3. Fuel ignites at end of plume, and forms the flame. We follow together, flame definition. See this figure. A large volume of very hot gases, controllably generated. Flame temperature. Flame temperature is affected by 1. O2 level. 2. Secondary air temperature. 3. Type of fuel. See this table. Flame heat transfer rate. 1. Rate at which calories are exchanged to the material, load, coating, and refractory. 2. Heat transfer mechanisms by 1. Radiation from flame to load. 2. Convection from kiln gases to load. 3. Conduction from refractory and coating to load. Flame shape. Shapes. 1. Short. 2. Long. 3. Snappy. 4. Lazy. Shape controlled by 1. Type and position of burner. 2. Type of fuel. 3. Primary air, axial, swirl air, impulse. 4. ID fan flow, secondary air temp. 5. O2. Flame shape. Goal. The shortest and highest temperature flame without adversely affecting clinker quality, coating formation, ring formation, refractory life, or causing damage to rotary kiln discharge area. A hot flame is always shorter than a cold flame. Always wait for a stable rotary kiln to make changes to the flame shape, and discuss changes with other operators, and production management. Combustion. Kiln exhaust gases. 1. O2. 2. CO. 3. SOx. Combustion state, O2. Ideal O2 level determined from 1. Clinker quality. 2. Refractory protection requirements. 3. Shell temperature. Goals. 1. Keep O2 as low as possible. 2. Maintain constant O2, which maintains constant rotary kiln temperature profile. 3. Low CO. Combustion state, CO. 1. Can we accept some CO? Most plants operate with some CO, since it is difficult to achieve complete combustion of fuel. 2. CO caused by lack of combustion air, and poor fuel preparation, fineness, viscosity, mixing, process of pulverization. 3. Incomplete combustion lead to longer and colder flame. Combustion state SOx, SO2 and SO3. 1. Represents sulfur oxidation from all fuel types. 2. SO2 formation decreases, with more oxidizing combustion. 3. SO3 volatilization increases, with hotter burning zone and length of flame. 4. SOx reacts faster than CO, to changes in combustion. Summary. 1. Fuel plus air, lead to, kiln flame plus exhaust gases. C plus S plus O2, lead to, heat plus O2, plus CO2 plus SOx. 2. Combustion quality issues. Heat quality, calcination. Flame quality, clinkerization. 3. Keep O2 as low as possible, but too low O2 results in 1. Kiln instability. 2. Incomplete combustion, high CO. 3. Sulfur volatilization. 4. Short refractory life. 5. Poor clinker quality. Summary. 1. High O2. High SHC. Long flame. Possible production limitation. 2. SO2, is inverse of O2. Combustion goal. Short, hot flame, but beware of refractory life, with low O2, and low CO. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.